Hello friends. Yesterday we discussed about refraction. We know that when a ray of light enters from a denser medium to a rarer medium, then it bends away from the normal, right? And we also know that if a ray of light enters from a rarer medium to denser medium, that it bends towards the normal, right? Okay, now today we will discuss about real and apparent depth and total internal reflection, right? Now first topic is real and apparent depth. So we can say that real and apparent depth, right? Now friends, હવે તમે જ્યારે કોઈ રિસોર્ટમાં જાઓ અને એ રિસોર્ટમાં તમે સ્વિમિંગ પૂલ જુઓ, તો જે સ્વિમિંગ પૂલની સરફેસ છે એ સરફેસ તમને થોડીક ઉપર દેખાય છે, રાઈટ? એકચ્યુઅલ તો એની બહુ જ ડેપ્થ હોય છે, રાઈટ? બટ જ્યારે આપણે એ સ્વિમિંગ પૂલની સરફેસને જોઈએ તો એ જે સરફેસ છે એ આપણને થોડી ઉપર દેખાય છે, રાઈટ? તો આવું કેમ થાય છે? તો the reason behind this is real and apparent depth, right? Okay, now consider this figure here. Yes, here suppose this is tank or swimming pool. Here the bottom of tank at h2 depth, here we take depth h2, right? And here this is denser medium because here this is a water, right? So here this is the medium of water, right? So here this is water, right? So here I denoted by D. So this is a denser medium having refractive index N2, right? So here this is the bottom of the tank or swimming pool. Here consider this point O. Now here these are the two rays. This is our first ray, this is our second ray, right? Okay, now this is the normal. Now we already know when a ray enters from denser to rarer medium, then this ray bends away from the normal. So this ray bends away from the normal like this, right? Like this. But here when we saw normally, so we can see that these rays are meet at some point here. Here we can denote it O dash. So here when the bottom is viewed normally, the bottom O is observed at point O dash. So we can say that when the bottom is viewed normally, it is observed at O dash instead of O. Now If we view by some angle like this is the bottom O. Here consider this is the first ray like this is the second ray like this. Normal moves away like this. But in normal condition, when we see, so this rays meet at this point like this. So here we can view O dash instead of O, right? Like this. Okay. So we can write that. So here we can write that as so in figure, the bottom of tank is at H2 depth. Here you can see this in denser medium, right? So here we denote a denser medium. Refractive index having N2. So here this is rarer medium of air and refractive index is N1, right? So here N1. Okay. When the bottom is viewed normally like this here, as we see the bottom normally, it is observed at O dash instead of O. And when the bottom is viewed by some angle like this, so it is observed at O dash instead of O. So here this is our real depth, which is H2, and this is our apparent depth which is H1, right? Here this is H1. Okay. Now you have to remember the following formula. Yes, N, which is refractive index of rarer, to the refractive index of denser, which is equals to apparent depth upon real depth. So we can write that N1 upon N2 is equals to H1 upon H2. So friends, you have to remember these things. N1 upon N2 is equals to H1 upon H2. And you have to remember the following two sentences. The refractive index of air with respect to vacuum is 1.00029. You have to remember this. The refractive index of air with respect to vacuum is 1.00029. Due to this, difference between actual sunset and apparent sunset is about 2 minutes. So we can write that time difference between real and apparent sunrise and sunset is 2 minutes, right? So the sun is visible a little before the actual sunrise until a little after the actual sunset. This is due to refraction, right? So we can say that due to refraction, the sun is visible a little before the actual sunrise and until a little after the actual sunset, right? So this is due to the refraction, and you have to remember the time difference, which is 2 minutes, right? Okay, now friends, we discuss about total internal reflection. So when light travels from denser medium to a rarer medium, at the interface it is it is partly reflected back into the same medium and partly refracted to the second medium. This reflection is called internal reflection, right? So what is internal reflection? So we can say that when a light travels from one medium to another medium, some part of light is refracted and some part of light is reflected. So this is known as internal reflection. We also know that when a ray of light enters from a denser medium to a rarer medium, then it bends away from the normal, right? Okay. Now, friends, consider the following figure. Here, this is the interface between two medium. Here, this is our first medium. This is denser medium of water, and this is rarer medium of air. Now, here something, consider a source A, right? Okay. Now, suppose here this is one ray which is incident at 19 angle. So this is passed like this, right? We can see that. We already know about this phenomena. Now, suppose our first incident ray which is incident at the point here, something point here. This is our point O1, right? So here our incident ray is AO1. This is the normal. So here incident ray and normal. So this is our angle of incidence. Here we denoted this angle by I1. Right. We already know about internal reflection. Some part of ray is reflected and some part of ray is refracted. So some part of ray is reflected like this, right? And some part of ray is refracted. I repeat, some part of rays reflect like this and some part of ray is refract. So here denser to rarer. So this ray move like this away from the normal. Okay. Now we discuss about our second incident ray. As we increase the angle of incident like this, here you can see this incident ray AO2. Here angle of incident is I2. So here as the angle of incident increase, so the angle of refraction is also increase like this, right? So this is refracted ray and this is reflected ray. Now we again increase the angle of incidence like this, I3. But at some value of angle of incident, the angle of refraction is 90 like this, right here, like this. Then this incidence angle is known as the critical angle. So we can say like this: the angle of incidence for which the refraction angle become pi by 2, then that incidence angle is known as critical angle. As if the angle of incident increase still further, we can say that greater than the critical angle, then refraction is not possible. So incident ray is totally reflected. So this is known as total internal reflection. So as we increase the angle of incident greater than critical angle, you can see from the figure here, this is I3 is equals to IC, which is critical angle. So here if angle of incident greater than critical angle, then refraction is not possible. So the incident ray is totally reflected like this, and this is known as total internal reflection. Okay, I repeat. First of all, what is internal reflection? So we can say that when the light travels from denser medium to rarer medium at the interface, it is some part of ray is reflected and some part of ray is refracted. This is known as internal reflection. We also know that a ray of light enters from a denser medium to rarer medium, then it bends away from the normal. Now see here, this is a denser medium, this is the rarer medium, denser medium of water, rarer medium of air, right? Okay, now here suppose this is the source, AO1 is the incident ray, right? So here I1 is the angle of incident. Some part of ray is reflected and some part of ray is refracted. As we increase the angle of incident, angle of refraction also increase. So as we increase the angle of incident, at some value the angle of refraction is become 90. This angle of incident is known as critical angle. And then if angle of incident is greater than the critical angle, then refraction is not possible. Then incident ray is totally reflected. This is known as total internal reflection. Okay, so we can write that as shown in figure, incident rays AO1 is partially reflected and partially refracted. As the angle of incidence increases, the angle of refraction also increases. The angle of incidence for which the refraction angle becomes pi by 2, then that incidence angle is known as critical angle. Here like this, you can see in this figure. Now, as the angle of incidence increases, as I greater than IC, then refraction is not possible. So incident ray is totally reflected. This is called total internal reflection. Here you can see that as I is greater than IC, then refraction is not possible. So the incident ray is totally reflected. This phenomena is known as total internal reflection. Okay, now here consider this point as O3, right? So here angle theta 1 is I3, or we can say IC, which is critical angle, and theta 2 90. Here we can write that this is 90. So here at point O3, we applies a Snell's law, right? So we can write that according to Snell's law at point O3, right? Here we know Snell's law, n1 sin theta 1 is equals to n2 sin theta 2, right? So we can write that n1 sin theta 1 is equals to n2 sin theta 2. So n1 sin, see here, theta 1 at point O3, theta 1 is I3 or IC, which is critical angle, and theta 2 is angle of refraction, which is 90. So theta 1 is equals to IC and theta 2 is equals to 90, right? So n1 sin theta 1, which is IC, is equals to n2 sin theta 2, which is 90, right? Okay, now we know the value of sin 90. Sin 90 is equals to 1. So we can write that n1 sin IC is equals to n2, because sin 90 is equals to 1, right? Okay, now here we take n2 to left hand side, so we can write that n1 upon n2 into sin IC is equals to 1. We know that n1 upon n2 is equals to n12, right? So n12 sin IC is equals to 1. We know that n12 is equals to n1 upon n2. So what is n12? So we can say that refractive index of medium 1 with respect to medium 2, right? Okay, here so we can write that n12 is equals to 1 upon sin IC, right? So you have to remember this formula, n12, which is refractive index of medium 1 with respect to medium 2, is equals to 1 upon sin IC, right? Okay, here we denoted by this as equation 1 and equation 2. Here from the figure you can see that our first medium is denser and second medium is rarer. So here denser medium, which is water, refractive index is n1, and here rarer medium of air, refractive index n2. We know refractive index of air is 1, right? So we can write that from equation 1, right? Okay, n1, so n1 as it is upon n2, value of n2 is 1, into sin IC is equals to 1. So we can write that n1 sin IC is equals to 1, right? So we can write that sin IC is equals to 1 upon n1, or we can also write that n1 is equals to 1 upon sin IC, right? So here you have to remember this equation, n1 is equals to 1 upon sin IC, right? Okay, so you have to remember the following formula. First formula, which is n12 is equals to 1 upon sin IC, right? Here n12 is equals to n1 upon n2, right? Value of n1 as it is, value of n2 1. So we can write that n1 upon 1 sin IC is equals to 1. So n1 sin IC is equals to 1. So sin IC is equals to 1 upon n1, or n1 is equals to 1 upon sin IC. Okay friends, This equation is very useful for your examination. Suppose I give refractive index of any medium and you have to find out the critical angle, right? So for this you have to remember this equation, n1 or n is equals to 1 upon sine IC. Okay, thank you.